This lesson's on special right triangles. Our objectives here are to recognize the special right triangles in a variety of different problems and to find the lengths of the different sides of those special right triangles. There are two types of special right triangles we'll be focusing on in this lesson. The first one is called a 30, 60, 90 right triangle. The second one is called a 45, 45, 90 right triangle. They are named according to the angles involved in the triangle. There are some key shapes that are tied to these special right triangles, the 30, 60, 90s. We will be using them quite often when we get into our area unit and volume unit for finding the altitudes of an equilateral triangle. The altitude of an equilateral triangle is equal to the length of the long leg in a 30, 60, 90 triangle. And then 45, 45, 90s are used to find the diagonal of a square. The diagonal of a square is equal to the hypotenuse of the 45, 45, 90 triangle. Let's focus on 30, 60, 90s right now. So these triangles are important because of their relationship to an equilateral triangle. You can see here we have an equilateral triangle drawn. All three sides are equal. All three angles are equal. Each angle is equal to 60 degrees. Now what happens here is if we add an altitude to our equilateral triangle, we now have enough congruent parts between the two triangles created. We got one on the left, one on the right, to show that those two triangles are congruent. You could say they're congruent by angle side or by a hypotenuse leg relationship. Now, according to CPCTC, or the corresponding parts of congruent triangles are congruent, we can now conclude the following characteristics of these two triangles. We can show that we got a 90-degree angle here, a 60-degree angle here, which allows us to say that both of these have to be 30-degree angles. So the altitude is not just an altitude forming a right angle with the bottom of our triangle here, but it also serves as an angle bisector up on the top. So we got 30 degrees on both of those. We also know that this altitude is, besides meeting at that 90-degree angle, it also bisects that bottom side, meaning this segment here from corner to midpoint is the same distance as it is from this midpoint to this corner here, because those are corresponding parts of our two triangles now. So this allows us to set up our shortcut or our pattern that we're looking at for our 30, 60, 90s. So for this pattern, what we're going to do is we're going to focus on one of our 30, 60, 90 triangles. So we're going to focus over here on the right-hand side. So let's create that rule here. So to create that rule, what we're going to do is we're going to make our long side here 2x. The reason we're going to make it 2x instead of just a single x is that we're just avoiding fractions. So to avoid fractions, I know we're going to have to cut this side in half. So we're going to just double it in size, giving us that option to not have a fraction involved with our rule. So if this length is 2x, that means from corner here to the bottom left corner here would also be 2x. If we divide that in half, like I was talking about, that gives us a single x value for that bottom part. That single x is always going to be across from the 30-degree angle. The 2x is always going to be across from the 90-degree angle. So to find that third side, the side that's the length of the altitude, what we would use here just to set this up to find that rule is we would use Pythagorean theorem. So in Pythagorean theorem, our height would be one of our legs. This length right here, this x would be a second leg, and the 2x is our hypotenuse. So if we plug in the values in the correct spots, we get x squared plus b squared equals 2x squared. When we square the 2x, we got to make sure we square both the 2 and the x. Subtract x from both sides, giving us 3x squared. Square root both sides. Now we need to simplify that answer down a little bit. We have an answer, square root 3x squared, but it can be simplified down. So we're going to simplify that radical, break it up to a perfect square. Our perfect square here is the x squared. The other part of it would be the 3. The square root of x squared simplifies down to just a single x. This x root 3 is our rule that we're looking for the height or the long leg of the 30, 60, 90 triangle. What we want to make sure of as we start to get into the 30, 60, 90 triangles more is that we can put the rules in the correct position on each triangle. One thing you need to notice is when we talk about a 30, 60, 90 triangle that you have 3 different angle sizes. And what we learned earlier on when we introduced triangles was that if you have 3 different angle sizes, you have 3 different side lengths, and they correspond with each other nicely, where the smallest angle is across from the smallest side, largest angle is across from the largest side, and it keeps going from there. So now we have a 30-degree angle, which is our smallest, 60-degree angle, which is our middle-sized angle, and a 90-degree angle, which is our largest size angle. We have 3 different side lengths. We got x, which is truly a 1x, x root 3, which is 1.73 root or times x, and 2x, which is obviously 2 times x. The thing that people got to remember on this, or students need to remember, is that root 3 is not a value of 3. It's actually a value of 1.73. Because of that square root, it's a little bit deceiving, but keep this in mind that you are square rooting that number for the value. So the x is your smallest length, the x root 3 is your middle-sized length, and the 2x is your largest length. So when we go to our triangle here, what you have here is your short leg is always across from the 30-degree angle. The x, the shortest side length, is across from the 30-degree angle. The long leg, which is a little bit deceiving because of the word long, but it's the longer of the 2 legs, it's the middle side length overall, is always across from the 60-degree angle. So middle angle, middle side length. The hypotenuse is always the longest side in a right triangle, so that always has to be across from the 90-degree angle. So our longest side, which is a 2x, is always going to be across from our largest angle, the right angle. In this example, what we're looking at doing is they give us a 30, 60, 90. We recognize that it is a 30, 60, 90 because we know that all 3 angles of a triangle add up to 180. They give us a 90 here. They give us a 60 here. The only possible measurement down here that angle could possibly be is a 30-degree angle. So being that this is our smallest side, we know that this is our smallest angle, which is why we know that we're given a short leg. So when I go to approach a problem like this where I'm trying to find A, which is our long leg, or B, which is our hypotenuse, would be to first label our rules inside that triangle so I know which rule goes with what side, and that helps me to not make simple mistakes. So I know since this is a 30-degree angle, this has to be 1x because that's my smallest side length. The 90 is my largest angle, which means the hypotenuse here has to be my longest side rule, which is 2x. This is my middle angle, so my middle side rule is x root 3. So to start the problem, we're looking at our short leg here. What I like to do is I like to take my value and make it equal to the rule. When they give you that value on that side, just make it equal to the rule and then try to find out what x is equal to. This one's pretty simple. It's pretty straightforward because you're just making 12 equal to x. It'll get more complex as we look at some of the other examples. Now, once we have that x value, we can go to our other side lengths. So we're going to go down to our long leg next, take a look at our rule, which is x root 3, and we're going to take that x value from our short leg or our initial side, and we're going to do a simple substitution. We're going to substitute the 12 in for the x, which gives us 12 root 3 as an answer. So our long leg length would be 12 root 3. Then we would move on to our hypotenuse. We would take a look at our rule, which is 2x, plug the x value in, which is 12. So that gives us a 2 times 12, which gives us a hypotenuse value of 24. So our hypotenuse value is 24. And we have now solved that triangle just based off of recognizing a 30, 60, 90 with a short leg of 12. In this example, what we have here is we got a little bit different situation. We have a hypotenuse value of 4, so we're starting off with a hypotenuse. Our goal is to find the short leg and the long leg of that 30, 60, 90 triangle. Again, we know this is a 30, 60, 90 triangle because we have a right angle here. We have a 60-degree angle here. The only other possible angle that we could have is a 30 down in this corner because these have to add up to 180 degrees. To start off, first thing I would do is I would write in our rule. We know that our short leg is a value of a. Our hypotenuse has a value of 2x, and our long leg has a value of x root 3. So now we're going to start off with our hypotenuse, since that's the one we're given a value of. We're going to set our value equal to our rule, so 2x equals 4, and our goal is to find out what x is. So our x value in this problem is going to be 2. My first move always when I'm starting from the hypotenuse, or if I'm starting from the long leg, is to find that short leg first. So after I got the x value for the hypotenuse, I go to the short leg. My short leg rule is x. So simply if I replace x with 2, my value for my short leg is going to be 2. Now I can move on to my long leg. My long leg has a rule of x root 3. If I take my x value of 2 and plug it in here, that gives me 2 times root 3 as an answer, or more simply 2 root 3. So that would be my answer for my long leg. So when I have a hypotenuse of 4 in a 30, 60, 90 triangle, I'll have a short leg of 2 and a long leg that's equivalent to 2 root 3. This sample is another example of where we're given a hypotenuse value, but this time instead of having an even value, what we have is an odd value. This will be the exact same process that we did in the last example. The only difference is you need to be comfortable with leaving some answers in fractional form. Okay, sometimes you might see them in decimal form, but for the most part, from what my experience, most authors leave them in fractional form. So to start this off, we're going to look at our rule again. So we got our x here, our 2x for our hypotenuse, and across from the 60 we have our x root 3. We're going to start off by looking at our hypotenuse. We're going to set our rule equal to our value, so 2x equals 7. Now when we divide both sides by 2, we're going to leave it as 7 halves. 7 halves is an acceptable answer for a side length, and you'll see that type of answer on a majority of your standardized tests that you're going to take to get into college. So moving to our short leg, our short legs rule is just simply x. We do our replacement or our substitution, tells us our x value is 7 over 2, or 7 halves. So our length here is 7 halves. Now for our long leg rule is x root 3. We're going to substitute in the 7 halves for the x, which gives us 7 halves times root 3, which would be 7 halves root 3 as an answer. Now, you might also see 7 halves root 3 written as 7 root 3 over 2. Please understand that 7 halves root 3 and 7 root 3 over 2 are the exact same fractions, because this is truly a square root of 3 over 1, which would be 7 times square root 3 over 2 times 1, which would result in this format right here. These two formats are the same problem, or the same answer. As we move forward, you're going to find that there are going to be times where when you're solving for x, that you're going to have to divide by a square root. Now, according to rules of mathematics, it is considered improper to leave the square root in the denominator of a fraction. So to move the to move the square root out of the denominator of the fraction, you need to understand a process called rationalizing the denominator. This means you're going to multiply a fraction by a form of 1. The reason you're going to multiply by a form of 1 is that when you multiply a number by 1, it doesn't change the value. But you're going to disguise that 1 as a fraction, and you're going to see that as we go through this. As long as the top and the bottom of that fraction are the same when we multiply, we're not changing the value, we're just changing the look of that problem. So let's move on here to a sample. So here's a sample here. We got x equals 4 divided by root 3. To get that square root out of the bottom of this problem, what we're going to do is we're going to multiply this by 1. But we're going to disguise that 1 as root 3 over root 3. The reason we decided to do root 3 over root 3 is because if we take square root 3 times square root 3, that equals the square root of 9, which gives you a value of 3. It gives you a number that you can square root, or a perfect square. So it allows us to get that square root out of the denominator of the fraction and moves it up to the numerator. So what we get as a final answer to this would be 4 root 3 on the top, and root 3 times root 3 eventually ends up equaling a 3 on the bottom, making this the proper form of 4 divided by root 3. Here's another sample here. We have 18 divided by root 3. So we're going to multiply this again by root 3 over root 3. The reason we chose root 3's over here to symbolize our 1 is because we have to multiply root 3 times root 3 to get rid of that square root symbol in the bottom. So on the top we have 18 root 3, 18 times root 3, and then on the bottom we have root 3 times root 3, which is 3. Now this one's a little bit different because we have an 18 in front of the square root and we got a 3 in the denominator. Those two numbers do divide. The deal with this is if you have a number on the bottom, we want to divide numbers with numbers or roots with roots. But what we can never do is we can never divide a root with a number. So we can simplify down the 18 and the 3 to give us a final answer of 6 root 3, which is the 18 divided by root 3 in proper form. They both have the same value, but this is proper formatting. Here's our next sample of a 30, 60, 90 problem. On this problem, we want to find the short leg, which is S, and the hypotenuse, which is T. To start this off, we're going to start it off like we have every other 30, 60, 90 problem by looking at where our rules sit. Here's our 30-degree angle, here's our X, here's our 90, here's our 2X, here's our 60, and here's our X root 3. Small across from small, middle across from middle, large across from large, putting everything in the correct positioning. So now we're going to take in this problem and we're going to do what we've done in the last few examples, and we're going to make our rule equal to the value that they gave us. So the value they gave us is on the long leg, so we're going to take our rule for the long leg, which is x root 3, and make it equal to 12. Now what we're going to do from there is we're going to try to solve this for x. Now on this, it's going to take a little bit of time to show you the step-by-step what's going on here. Eventually we want to get to a point where we can just jump from this length being 12 to this answer right here being 4 root 3. So to get there, what we need to do, and the thought process behind it is, we're going to divide both sides by root 3. The reason we're going to divide is because this is multiplication over here. To get rid of multiplication, we divide both sides by the same number. So we're going to divide by root 3. That cancels out the root 3's on the left side of this equation. And we end up with a 12 over root 3. Now what we just got done talking about on the previous slides was how to rationalize that denominator. So we have 12 divided by root 3. We're going to multiply that by root 3 over root 3, which is a value of 1. And we're just changing the look of the composition of this fraction. So we end up with 12 times root 3 on the top. Root 3 times root 3 gives us a value of 3 on the bottom. This is something we can simplify. We can divide number with number. So 12 divided by 3 simplifies down to a single 4, and that's where I got the 4 root 3 for that missing side up here. So S is 4 root 3. Now to find that short leg, oh, I jumped ahead a little bit. So our short leg's shortcut is X. If we substitute that in, that's pretty simple substitution. I'm just kind of going above and beyond showing my work down here. That's where our 4 root 3 comes in for the short leg. We knew that from here. All right, so now moving on to the hypotenuse. Now that we know x, we should be able to find the hypotenuse just fine. Our hypotenuse rule is 2x. So we take our x value, we plug it in or substitute it in for the x here. That gives us 2 times 4 root 3. Again, we're multiplying numbers with numbers. We're not combining numbers with roots right now. So 2 times 4 gives us an 8, and we're looking at 8 root 3 as our length of our hypotenuse. This is a good example of when the long leg is a multiple of 3. When it's a multiple of 3 as a long leg, you're going to be able to simplify it like we did here with the 12 root 3 over 3 reducing down to a 4 root 3. You're going to see this pattern when we have a multiple of 3 there. In this example, we're starting off with a value on our long leg again, but the difference between this one and our previous example is that this long leg's value is not a multiple of 3. So it's going to have a different look to it. So we need you to kind of get used to the idea that your final answers in these types of problems might have a little bit of a different look to them that you're used to giving for answers. So let's take a look at what this looks like. To start this off, what we're going to do is, like we've done in the past, look at our rule. So here's our small angle. Our small side rule would be x. Our large angle and our large side rule would be 2x. Our middle angle and our middle side rule would be x root 3. We're going to start off here by taking a look at this, making our value that they gave us equal to the rule. So our long leg's what we're looking at. Our rule for our long leg is x root 3. We're going to make that equal to 5. We're going to solve this down by dividing both sides by square root 3. That gives us the square root 3's that would cancel out. We got 5 divided by square root 3, which we know we have to rationalize the denominator on. So we're going to multiply that by square root 3 over square root 3. That's going to give us a 5 times root 3 on the top and root 3 times root 3 on the bottom, which gives us a value of 3. Here's our x value, and this is the proper look for it, is 5 root 3 over 3. There's nothing wrong with leaving an answer like that. So now that we know what x is, we're going to look at our short leg. Our short leg's rule is simply x. So if we substitute that in, it tells us that our value for our short leg is 5 root 3 over 3. So there's our short leg's value. Now to find the hypotenuse, our rule is 2x. So we're going to take this value of x, which is 5 root 3 over 3, and plug it in for the x. That gives us 2 times 5 root 3 over 3. And when we multiply a fraction by a number like 2, we are just doubling the number on the top, not the root, just the number. So 2 times 5 root 3 ends up giving us a 10 root 3 over 3 for an answer. And that's what we're looking at up here for our value of t, or our hypotenuse. For this, what we're going to do is we're going to start to look at a 45, 45, 90 right triangle. These triangles come from splitting up a square by using a diagonal. So what we do is if we take a square like I have drawn here and we go from corner to corner, going through the interior of a square, what we've done is we've created two 45, 45, 90 triangles. The diagonal does bisect the opposite angles. So being that this angle up here in the square is a 90-degree angle, and the fact that a square is a form of a rhombus, the diagonal does some bisecting up here. So half of a 90-degree angle means both of those angles up there are 45-degree angles. Same thing holds true down in the bottom left corner. So we're going to concentrate on just one of these triangles. We'll look down here on the bottom right corner. Here's a redrawn figure of that bottom right corner of that square, giving us our 45, 45, 90 triangle. Now, this 45, 45, 90, because we have two angles that are the same, that means we have to have two sides that are the same. This is the converse of the base angle theorem, back when we talked about that theorem with isosceles triangles, because a 45, 45, 90 is a right isosceles triangle. So if we make this side here x because it's a side of a square, that means this side here, which is also a side of a square, has to be x also. Now what our goal is we got a nice simple rule for these two sides of this 45, 45, 90 triangle. Whatever this is it also. But we got to find what this missing part is here. So to find that hypotenuse, we're going to use Pythagorean theorem. These are our legs, so we're going to go x squared plus x squared equals our c squared, and that c squared, that answer for c, is going to give us our rule for the hypotenuse. So x squared plus x squared ends up giving us a 2x squared. We would then square root both sides. We have a perfect square right here, so we would break that up and go square root of x squared times square root of 2. The square root of x squared ends up giving us an x value times the square root of 2. So our rule for this side of a 45, 45, 90 triangle is the x root 2 relationship. Whatever this value is for x, you multiply by root 2 to get that hypotenuse length. Here's our first example of a 45, 45, 90 right triangle. We're going to start off with a sample where we're given a leg. Notice here we got a 45-degree angle and a 90-degree angle. That dictates that this third angle that's missing is also a 45-degree angle, being that our angles have to add up to 180. So like we did with the 30, 60, 90s, we're going to start off by looking at our rule. Which side goes with which rule? So we know that this side is our x rule. This side is also our x rule. And our hypotenuse is our x root 2 rule. So really it's not too complicated because two of the sides are the same. The two sides that are the same are the sides that are across from the 45-degree angles. The x root 2 is the longest rule, or the longest side rule. So that goes across from the 90-degree angle. So we start off here by looking at the leg. We're going to make the leg equal to the rule like we did before. X equals 5. So that tells us not just that this leg is 5, but our other leg is also 5. Now to find our hypotenuse, we take a look at our rule, which is x root 2. We substitute in the x value, which is 5. That gives us 5 times root 2, which is 5 root 2. And that's our hypotenuse. In this sample of a 45, 45, 90 right triangle, what we're given here is we're given a hypotenuse value. This hypotenuse value is example of one that is an even value. There is a difference between the even valued hypotenuses and the odd ones. So keep that in mind as we go through this problem. So what I would do first here is I would set up our rule for our sides. Taking a look here, we got a leg length that is x, a leg rule here that is x, and our hypotenuse rule, which is x root 2. To start the problem off, we're going to start where our value is. We're going to make our value equal to our rule. Our rule is x root 2. So x root 2 equals 16 is our equation. We're going to solve that for x. So to do that, we're going to divide both sides by root 2. So our root 2's here, x root 2 over root 2. The root 2's would cancel out, and we end up with a 16 divided by root 2. That gives us a denominator that we have to rationalize. Now this is a little different than the 30, 60, 90s because we're dealing with a root 2 in the denominator instead of a root 3. So being that this is a root 2, that form of 1 that we multiply by is now root 2 over root 2 instead of root 3 over root 3. The reason we do that is because on the bottom we want root 2 times root 2, which is going to give us a value of root 4, which is 2. And on the top we have 16 times root 2. So 16 times root 2 is 16 root 2. Root 2 times root 2 is root 4, which equals 2. Now we have numbers here 16 and 2 that are reducible, so we're going to reduce that down. That gives us a value of 8 root 2 for x. Our legs, our shortcut for our leg is simply x, so we know what x is. X is 8 root 2. We simply put that in for the x value, giving us 8 root 2. And both of our legs have the same value, so they're both 8 root 2 for this example. In this example of a 45, 45, 90 triangle, we're given the hypotenuse again, but this time the hypotenuse is an odd value, so this one is not any more difficult than the previous one, but it has a different look to it like we talked about before. So we're going to set up our rules. We have our x rule here, and our x root 2 rule here for our hypotenuse. Our hypotenuse is where our value is, so we're going to set up our value equal to the rule. 9 equals x root 2. We're going to divide both sides by root 2. The root 2's here cancel out. We're going to take that 9 divided by root 2 and we're going to rationalize the denominator, which means we're going to get that square root out of the denominator. We're multiplying that by root 2 over root 2. So along the top we have 9 times root 2, which is going to be 9 root 2. And we have root 2 times root 2 on the bottom, which gives us a value of 2. So our x value is 9 root 2 over 2. We're going to leave it alone at that because 9 does not divide by 2 evenly. It leaves you with a decimal. So this is going to be our proper fractional form of our answer for x. Now our legs, so we take a look at our legs rule. Our legs rule is just simply whatever x is equal to is the length of our legs. So 9 root 2 over 2 is going to be our value for x, which means both of our legs have a value of 9 root 2 divided by 2. Our goals here during this lesson was simply to recognize the 30, 60, 90 triangles and the 45, 45, 90 triangles within the different problem sets. But more importantly is once we do recognize those, we want to be able to use the patterns to quickly find the missing side lengths of these triangles. Now in my demonstrations here, I went through in extreme detail of how to find the missing values of these. We do not want these problems to take as long as what I demonstrated in this example, in these examples. What I want you to be able to do is I want you to be able to look at the one side and get the other two missing sides probably within a minute or so. It should not take you very long once you get the hang of these patterns. And this whole lesson is based on the idea of recognizing patterns and reacting to those patterns quickly. So keep that in mind as you're working through and look for different patterns that you see and try to develop a sense of what the different sides are when they give you one side of either a 30, 60, 90 right triangle or a 45, 45, 90 right triangle.